All right, I'd like to welcome Sean McGuffey to the podium. He's a senior engineer at Porter McGuffey Incorporated in Lawrence, Kansas. He's active in the American Society of Engineers, pressure vessels and piping division, as well as authored and co-authored over 15 papers and presentations on the use of CAE tools in engineering process. Would you please welcome Sean McGuffey to the podium?
Thank you. All right, well, my presentation has a very long title, so I won't read that out to you. But basically what we're going to cover is using CFD tools coupled with basic engineering to predict long-term, 9-year operational characteristics on a waste heat boiler. Nope, went forward one too many. As a quick overview, we're going to start from the beginning. What is a sulfur recovery unit? What is a waste heat boiler? How do they operate within a sulfur recovery unit, which is the primary focus of this talk today? Known modes of failure for waste heat boilers, the current condition that we are charged with analyzing, and then basically get into the details of how we analyze the condition and how we develop limit curves for future boiler operation. What is a sulfur recovery unit? Well, a sulfur recovery unit is used to recover elemental sulfur from process streams that contain hydrogen sulfide. And you'll get that in refining industries and chemical process industries, basically anytime you're dealing with anything that you take out of the ground. They primarily consist of a thermal reactor, a waste heat boiler, and primary and secondary condensers. I'm not a chemical engineer, so I'll just go very, very quickly through the elemental reaction that takes place. You bring in hydrogen sulfide, react it with oxygen, you produce sulfur dioxide and water. Then 2 molecules of hydrogen sulfide react with the sulfur dioxide. You get pure elemental sulfur and excess water. Some things to keep in mind with SRUs: the gas is reacted substoichiometrically. That'll become important in a minute. The reaction's very exothermic. We produce temperatures between 2200 and 2800 degrees Fahrenheit. That's basically dependent on the process streams that are coming in for the reaction, what the compositions are. Because we are reacting substoichiometrically, the reaction does not complete, and we typically have 3 to 5% mole of hydrogen sulfide remaining in the gas stream. The gas stream then enters the waste heat boiler, what we'll be talking about, to be cooled primarily. The gas cannot enter the condensers above about 700 degrees Fahrenheit. As a secondary, you get steam out of your waste heat boiler at 500 to 650 psig. That can be used for plant purposes, power equipment, power processes for heating and stuff. Basic overview of waste heat boilers. They're what's known as a fired tube boiler. If we can see with the laser, that's not really showing up too well. But what we see on the left-hand side in the dotted lines is a thermal reactor. That enters through what's known as a crossover into the hot pass of the waste heat boiler, travels down the waste heat boiler, makes a loop through the second pass, and then exits to the condensers. And one thing to keep in mind, and we'll see the geometry of it, is when we are entering on the hot pass, as I said, the gas is between 2200 and 2800 degrees Fahrenheit. The hot pass entrance at the tube sheet is ferro-lined, ceramic ferro-lined, to protect the steel. Obviously, the steel would melt at temperatures in that range. And let me make sure I didn't skip one. Okay, so now known modes of failures for waste heat boilers. There's 3 primary known modes of failures. The first is over temperature. The refractory, which is thermal protection within the boilers, we are using alumina-based refractory. It's good up to about 3,000 degrees Fahrenheit. You go much over that temperature, and you will almost immediately either crack or melt your refractory. The unit has to be brought down immediately and serviced. Sulfidation corrosion, which we'll go through a few slides on, is a long-term failure mode. It's a corrosive failure mode that will happen on the steel in the boiler at temperatures, and that is due to the sulfur in the process gas. As I mentioned, the process gas will be 3 to 5% mole coming through the boiler. And then the third failure mode is what's known as departure from nucleate boiling, film boiling occurring on the outside of the tubes. If this occurs, it's a short-term failure. It can happen in minutes. It can cause high temperature creep failure of your tubes, loss of your pressure boundary in the boiler, and the unit has to be immediately brought down. If we take a look on the left-hand side, what we see is what's known as a Cooper-Gorman type curve. These are developed from industry experience, and coming across the x-axis is the operational temperature of the metal in degrees Fahrenheit. On the y-axis are mole percent of hydrogen sulfide in the gas stream, and we're, as I said, operating at about 3 to 5% mole hydrogen sulfide, so we're up at the top portion of this curve. And for all the different curves that we see coming across, that represents higher and higher corrosion rates in mils per year. These tubes are typically about 160 mils thick, so you can see once we get up into the 800 to 900 degree operating range with the hydrogen sulfide content that we have, we can, within a period of a year or two, significantly corrode the tubes. What we can see on the right-hand side is what hydrogen sulfide corrosion looks like. Basically, you sulfide the steel, which embrittles the steel due to thermal cycling that goes on in the boiler. That embrittled steel will tend to flake off, as we see in the picture, and you'll lose your mechanical integrity of your tubes. Now, if we come into departure from nucleate boiling, as I said, was a short-term failure. What we see at the top of the slide is a typical heat flux versus wall superheat, or the temperature between the metal and the water on the water side of the boiler. And obviously, as we've seen in most textbooks, for a period of time as our wall superheat increases, our heat flux increases until we reach a maximum heat flux. Once we pass that maximum heat flux, the wall temperature will continue to increase, but the heat flux that can be transferred through the boundary decreases. And this is due to a film, a gas bubble forming on the outside of the tube, and so you're no longer convecting into liquid, you're convecting into a gas. A thing to consider with this curve that I like to point out with this curve is once we come over the top of the peak, that becomes conditionally stable, because on the process side, on the gas side of the tube, we are still transferring essentially the same amount of heat flux through the tube, but we're reducing the ability of the tube to pass that onto the shell side of the fluid. And so our temperature will continue and continue to rise. If your temperature gets up into the 1100 to 1400 degree Fahrenheit range with our 500 to 650 psig boiler pressure, will reach short-term creep failure, which we see on the tubes on the bottom portion of the slide. And this tube dimpled in, and it's known from operation this occurred over about a 10-minute period. There's actually a crack that doesn't show up very well in this image, but that was a loss of pressure boundary. You started to flow water back into the thermal reactor. The water starts contacting the refractory, which is at 2800 degrees, and really bad stuff happens very quickly. The current condition that I'm really going to talk about today is a waste heat boiler that we did for a refiner client of ours. The waste heat boiler was replaced in kind in 2000, so basically they just swapped out a new waste heat boiler with the same design as had been operating since the early 80s. An eddy current inspection on the tubes in 2009 indicated that significant tube loss had occurred. Actually, the picture of the corroded tube that we saw earlier was one of the tubes that was pulled out of this boiler, and it indicated that retubing was required to make sure that there was not a unexpected loss of pressure boundary during operation of the boiler. Once they opened the boiler up and took a look at the shell side, the water side of the boiler, they indicated that significant fouling had occurred near the inlet to the boiler. The fouling, as they inspected it as best they could, coming in through the manways, consisted of both a hard and soft scale. Unfortunately, because you have to pull the tubes out through the tube sheet, all of the soft scale was lost as the tubes were being pulled out, and we couldn't get very good chemical composition data out of them. Our job was to determine why corrosion had occurred and mitigate future corrosion that could occur in operation of the boiler, and then develop operational limit curves. To do this, the first thing that we needed to do was model the process side of the boiler, the gas side of the boiler. That controls the amount of heat flux coming through, controls the maximum temperature in the boiler, and controls the amount of sulfidation corrosion that could occur. We needed to determine the cases that needed to be analyzed, and then extrapolate the process side data to the operational history of the waste heat boiler. If we take a look at the upper left-hand portion of this slide, we can see the basic geometry of the inlet of the boiler. We have several layers of refractory. The ferrule that comes in, shown in the light green, that terminates. The pink is our gas space coming through. We took this geometry, developed a CFD model that you can see in the middle right-hand side, and then analyzed that at several process conditions. The most important piece of data that we can get out of this analysis is what occurs just downstream of the ferrule. Obviously, there's a sharp geometric discontinuity that introduces swirling and turbulent flow, and actually introduces a significant peak heat flux that occurs just downstream of the ferrule, which also corresponds to your peak temperature. And the next thing that we had to do was determine the cases that we needed to analyze. It's known from industry that there are several factors that affect your firing temperature and your maximum heat flux. The first is obviously the mass flow rate of acid gas, or the process gas coming through the stream. The composition will affect the chemical reactions that occur beyond the primary chemical reaction. We, in the boiler industry, refer to a term as pseudo duty, which is feed rate times the inlet temperature. And that gives a good overall indication of the duty that you're putting into the boiler. And then obviously your oxygen concentration and how close to stoichiometric firing that you are running at. We indicated that there were 4 process points of interest from the distributed control system: average air only, maximum air only, a low CO2 case, which again controls the reactions that are occurring, a maximum oxygen enrichment, and then we found that we always run a case that is 10% greater than any of the cases that we've run, just to bound what the maximum heat flux during service could be during a process upset. Once we performed the process side CFD modeling, we came in and performed curve fits, and in our case, linear fits of the maximum peak heat, or the peak heat flux just downstream from the ferrule versus the pseudo duty, mass flow times temperature. We see 2 curves here because they were replacing the ferrule geometry with the new retubing effort, which I'm not going to discuss today very much. We then performed a second series of fits, and we found that we could linear fit peak heat flux versus the peak tube temperature versus the peak flux, or basically the second derivative. What we did then is we coupled those curve fits with MATLAB data, with a MATLAB routine. The MATLAB routine took an Excel data book that was recorded in the historical archives from the refinery, that recorded the volumetric flow rate, the pressure, temperature, firing temperature is recorded, converted that to the mass flow rate just through basic thermodynamics, and used our curve fits, time integrated, to predict the peak tube temperatures versus time, which we see in this graph. And the next thing, because fouling had occurred, is we needed to account for fouling and what the effect of fouling could be. If you go to literature, fouling growth can be represented by the basic fouling growth equation, which is basically a set of constants times this quantity, which has a linear time term and an exponential time term. If we review that equation very quickly, fouling can grow linearly with time, exponentially with time, asymptotically with time, or it can actually decrease with time, depending on the choice of constants. And I've shown just a couple of fouling growth regimes on the right side of the slide. To take the fouling resistance and convert that to how it might affect the internal temperature of the tube, we then went back to first principles of thermodynamics. If we assume that the radius of the outside radius of the fouled tube is proportional to the square root of the mass, or volume, then we can develop a new conductive resistance for the fouling. We know that the convective resistance on the outside of the new radius is just represented by our second equation, we can combine those and come up with a new external heat transfer coefficient. And if we take our fouling growth equation, walk it through the other equations, we get a new external film coefficient versus time, as we see in this plot. We then updated the MATLAB routine. We then ran the process side models and varied the outside external film coefficient on the process side models to find a relationship between the external film coefficient and the multiplier on the internal tube temperature. And what we found is actually if you plotted the inverse of the multiplier by the effective coefficient, you can see that makes a very nice power law fit. We could then take that and implement it into our MATLAB routine and determine our temperature multiplier versus time, and run several cases with different fouling regimes. Linear growth, asymptotic growth. What our client was primarily concerned with is that they didn't have one-off instances a few times during the operation of the boiler that caused all of this damage. And what we were able to show is that several of the curve fits all led to long-term boiler damage due to water quality issues and not short-term excursion events that could have occurred in the plant. The next thing that we needed to do to develop full process curves, operational curves for the boiler, is to take a look at the departure from nucleate boiling, determine how close they were. In this case, and once we look at the slides, they actually weren't that close, but this is a significant event for a lot of these boilers. They push them as hard as they can, and if one unit goes down, you have to switch immediately to another unit to keep from releasing the hydrogen sulfide into the atmosphere. To perform the departure from nucleate boiling modeling, and I'm not going to cover this in great detail, I'm going to wrap up with a few references of papers, and my boss, Mr. Porter, actually presented a very long paper at the Energy Conference earlier last year. It requires a transient volume of fluid model with the boiling model enabled. What we use it for is determine the margin of safety, how close we are with the heat fluxes that are coming through the tube to reaching that peak heat flux where we fall off the cliff, become conditionally stable, and can cause a short-term creep rupture failure. And then the last thing that I'll mention, and I have the reference of an ASME paper that I'll wrap up with also, we did develop the technology to modify the model through the use of some fairly complicated field functions to account for the departure of from a nucleate boiling event and to predict what the maximum rise in tube temperature is versus time. We built a model. Departure from nucleate boiling will only occur just downstream from the ferrule. Past that point, thermodynamic modeling, empirical modeling does a very good job of predicting how boilers are going to operate. It's only knowing what happens right downstream from the ferrule that is of concern. So we only include the first 3 feet on the hot pass, and then we transfer the process fluxes that we predicted from the periodic model into this model on the inside of each tube. You can see a blow up of the tubes in the upper right-hand corner using XYZ table data. Basically in MATLAB, we take our periodic process model, rotate it to get a full 360 degrees of data, and then translate it through space to create full XYZ table data to apply the heat flux on the inside of the tubes. As you can see from the upper right-hand side, it is a significant model. It's about a 24 million cell model, and the reason for that is that we have to get very refined in the boundary layer, both to fully capture the convective heat transfer that's occurring and also to allow for decent approximation of the nucleation of bubbles. What we found when we modeled this case versus a lot of the other cases that we've modeled is that we were fairly far away from departure from nucleate boiling. And one of the big reasons for this is that this is a 355 tube boiler where we normally are looking at about 155 tube boilers. And that gives a very long path through the tubes, a very long event for the water to have energy imparted from buoyant forces leading to high velocities, keeping us away from being able to form a stable film blanket on the tubes. And we took all of this information now and combined it develop operational limit curves for the boiler. The main thing for the operational limit curves, outside of all the information that we can derive from CFD, all the information that we'd love to have as analysts, is it has to rely on measurable process data. That's mass flow rate or volumetric flow rate, which can be converted to mass flow rate, and firing temperature. We have to consider the three regimes: refractory over temperature, long-term sulfidation corrosion, and short-term departure from nucleate boiling events. And then we have to combine the results of the analyses to develop the curve. And what we see here is the curve that we can develop. The blue line is our sulfidation corrosion curve. That's a long-term curve. If you stay below this curve in terms of mass flow versus temperature, you should not have long-term sulfidation corrosion problems, given a expected boiler life of 20 years. The red curve on the right-hand side is tube tip temperature limited. So that is where you will fall off the cliff, where you will have a departure from nucleate boiling event and possible creep rupture. And then obviously, once we hit 3,000 degrees, we're refractory temperature limited, and you can't go any higher than that. And with that, so to conclude very quickly, with the process side CFD models, we were able to predict the full 9-year historical operation of a waste heat boiler, something that we couldn't do with just a transient CFD. We were able to show that the fouling growth was long-term, not short-term process excursions, basically caused by water issues within the boiler, and could make recommendations related to the future waste heat boiler operation to prevent fouling from occurring on the shell side. And then we were able to also develop an operational limit curve for the boiler. And that does wrap it up. I'll leave that slide up if anyone wants to record. We've written 3 papers for ASME on the subject, which go into much greater detail than I could in 20 minutes. Thank you.
Do we have any questions?
You didn't get into the detail. When you model use CFD to model the heat, did you include combustion, radiation, all those things?
No, for the thermal reactor, we don't include the combustion. What we assume is the inlet temperature. Obviously, with a large boiler like this, and especially getting into models that are 24 million cells just for the inlet side of it, we assume inlet flow rates that are evenly distributed, temperatures that are the firing temperature, usually measured from a piece of equipment called an E²T, which is an infrared temperature sensor. We've done another project, and I haven't written a paper on it yet, where we did have to take a look at it was the mechanical interaction between the thermal reactor and the boiler, because obviously the thermal reactor is going to heat up quicker and introduce some bending stresses in. There we did have to we didn't include combustion because we knew the firing temperature, but we did have to model transiently the change in temperature of the gas flow through the thermal reactor and the radiation impingement on the inside of the refractory and how the metal temperature changed versus time.